Welcome to IHEA's first webinar in our new series on sustainability and decarbonization. On behalf of the Industrial Heating Equipment Association, thank you for joining us for today's webinar titled Thermal Process Carbon Footprint, presented by BJ Bernard with Surface Combustion. Before we get started, I'd like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them in the questions panel. The speaker will address questions at the end of our webinar. This webinar will be recorded and available in the sustainability area of the IHEA website within the next few days. All attendees will receive a brief survey after the webinar. Please take a few moments to reply. We appreciate your feedback as IHEA continues this critical initiative for the industrial heat processing industry. Now I'd like to introduce the presenter for today's webinar. BJ Bernard is a material scientist and executive with a passion for metallurgy and thermal processing. He's president of Surface Combustion, which continues to be at the forefront of thermal processing technology after 275,000 installations worldwide and 108 years of operation. BJ is experienced with a wide swath of processes for ferrous and non-ferrous materials using prepared atmospheres, vacuum, and ion plasma technologies. BJ loves helping customers find the optimal process and equipment for their metallurgical quality, production, and safety requirements. BJ is a past president of IHEA and the current chairman of the Center for Heat Treating Excellence at Worcester Polytechnic Institute. BJ, take it away.
Thanks very much, Kelly. Welcome, everybody. Hope everyone's having a nice morning so far. It's a beautiful day here in Toledo, Ohio. And wherever you are, I hope you're having a wonderful day as well. Topic for today, kicking off the IHEA Sustainability Initiatives webinar series with probably the most common question I'm getting these days. How do I calculate the carbon footprint of my thermal process? Most people will say of my heat treating process, of my furnace, of my oven, of just what I'm doing in my facility. And there's a lot of information out there that honestly can be very confusing. And so over the last couple of years, what I've been doing is trying to make it easier for some of my customers to understand exactly what they need to do when they get asked by their customers, what's your carbon footprint of your process that you're working for us? They have a good answer. It might not be the perfect answer, but something to start from. And then from there, they can also take the chance to act and reduce their carbon footprint. So what we'll do, we'll have looking at the agenda, we'll go over, hey, first, what's your carbon footprint? And why do we need to calculate it? Then how can we calculate it? Then finally, we'll talk about how we can reduce your carbon footprint overall. So to get started, we'll jump right in with some definitions, because if we don't have a common language, we don't understand for each other. So I want to make sure that I define some terms going right up the front, so we all understand what we're talking about going forward. First of all, carbon footprint, just at its base, is the amount of greenhouse gases emitted by somebody. You also hear the term called carbon neutral or net zero, and all that means is the greenhouse gases I emit, including carbon dioxide, equals the greenhouse gases I remove from the atmosphere. So you'll see a bunch of people who are net neutral, net zero, carbon neutral. They say they are. What they're doing is they're accounting for all the greenhouse gases they emit, and then they're either offsetting it or finding a way to remove the greenhouse gases they emit from the atmosphere. So that is how you become net zero. In general, the goal for most people isn't to become net zero, but we'll talk about the global goal right now is to reduce carbon emissions or greenhouse gas emissions by 50%. We'll talk about why that is in a little bit. Third, decarbonization. It's reactive removing greenhouse gases, mainly CO2, but it has to do with other greenhouse gases by a person, process, or organization. So when we're talking about decarbonizing, that's what we're doing. We're trying to move towards net zero, move towards carbon neutral from where we are currently with our carbon footprint. There's some other terms that are talked about these days: electrification, sustainability. Electrification is processing of substituting electric power for fossil fuel energy. And that is a common thing a lot of people are looking to do. During the course of this presentation, we'll talk about whether that's a good idea or a bad idea. In some cases, that's a really great idea. In other cases, that's a really awful idea if your goal is to reduce your carbon footprint. The sustainability, that's a big word and a word that's thrown about and bandied about quite a lot, but it really has to do at a very high level, on a governmental and even on a very high boardroom level. It all has to do with meeting the UN Sustainable Development Goals, which is kind of highbrow for this topic, but I just want to make sure that this is on the screen. So when people are talking sustainability, they're not just talking about decarbonization, carbon footprint. They're talking about ending world poverty. They're talking about ending world hunger. They're talking to make sure that everybody has a fighting chance in life. So that's when we're talking about sustainability, there's many, many more aspects to that than just decarbonization, making sure everybody has clean water, et cetera. And finally, what's a greenhouse gas? A gas, technically, it's a gas that absorbs and emits radiation and contributes to radiative forcing of global temperatures. Now, what do I mean by radiation? Radiation is sun's rays. The sun radiates light at the earth and then it bounces back into the atmosphere, and the greenhouse gases, instead of letting those rays bounce into space, the greenhouse gases absorb that radiation, radiates it back towards Earth, and has a warming effect, which is called radiative forcing. And these greenhouse gases, but the more there are of them, the warmer global temperatures will be. So first off, we're going to have a little trivia game. And if we have a little question box, and we want to make sure you know how to use it. So the question is, what's the most abundant greenhouse gas in the atmosphere? In your question box, if you go over there, you can try to type an answer and we'll give you a kudos if you get it right. And Kelly's going to take a look and see if anybody's got a good answer for what the most abundant greenhouse gas in the atmosphere is. Kelly?
Well, we're getting a lot of carbon dioxide right off the bat.
A lot of carbon dioxide right off the bat. Okay.
Yeah.
Anybody else? Anything else?
Got a nitrogen.
Nitrogen. Okay. All right. Well, that's good.
Nitrogen. H2O is in there.
Ah,
Maybe natural gas.
Okay, that's a good one.
They're figuring it out here. Water vapor.
All right. Well, let's go on. Well, that's some good guesses, and the actual correct answer is the stuff that's in those clouds, water vapor. Water vapor is a predominant greenhouse gas in the atmosphere. The reason being, we'll talk about it here, is it is a triatomic molecule. It has diatomic molecules like nitrogen and oxygen do not emit and absorb radiation that well. But any triatomic molecule, water vapor, carbon dioxide, sulfur dioxide, all absorb and re-radiate radiation. They are all greenhouse gases. And if you talk about carbon dioxide, there's about 415 ppm of carbon dioxide in the atmosphere. On any given day around the world, there's 894,000 ppm of water vapor in the atmosphere. But we're all very worried about carbon dioxide. And why is that? Well, over the last 250 and so years, since the start of the Industrial Revolution, it's been proven by taking Antarctic ice core samples that the level of carbon dioxide in the atmosphere has increased. So there we go. It's been increasing, and it's been pretty well proven, and the evidence is just there. Before 1750, the level of carbon dioxide in the atmosphere bounced between maybe 175 and 300 ppm for about 80,000 years. So we're well above that now. And so the question is, what does that mean? Well, the estimated natural removal rate of carbon dioxide from the air is 17.5 gigatons of CO2 per year. Right now, we're emitting about 35 gigatons of CO2 a year. So when you hear about the reducing our carbon dioxide emissions or our greenhouse gas emissions by 50%, that's what we're targeting. We're trying to get back to where the natural removal rate of the planet can remove the amount of carbon dioxide that we're producing. So if we have a goal of reducing our greenhouse gas emissions by 50%, the Earth can take care of itself. Now, okay, great, we're emitting carbon dioxide, but what does that mean? In general, we have also seen a trend that global temperatures have been on the rise, and we measured that with NASA, the Goddard Institute for Space Science measures that with the Global Land Ocean Temperature Index. And what they do is they've set a standard of 0 degrees between 1951 and 1980. But right now, we're operating about 0.8 to 1 degrees above that standard. So we've seen a warming effect in the atmosphere, and it happens to coincide with the amount of carbon dioxide that's increased in the atmosphere. Now, does that mean that carbon dioxide and greenhouse gases are the sole cause for global warming? No, because there's a correlation, but it's heavily implied that that's the case. So in the end, if we can find a way to reduce our carbon dioxide in the atmosphere, we'll hopefully reduce the amount of global temperature rise. So that is the goal, and that's why everybody's got so up in the air about carbon dioxide versus the ozone layer or something else these days, even though that's still a concern, but we don't hear about it as much. Whether this will be still a concern 20 years from now, we'll see. But right now, that's what people are looking to do. And governments and corporate boards of Fortune 500 companies are asking individuals and companies to figure out what their emissions are and what their carbon footprint is. So we're talking about, okay, what carbon footprint? Carbon dioxide is a greenhouse gas. Water vapor, I said, was a greenhouse gas too. The issue with water vapor is it comes out of the atmosphere relatively easily. It comes out as rain. CO2 kind of stays in the atmosphere. It doesn't come out very easily. You don't see snow made out of dry ice very often. So the only way to get it out of the atmosphere is for it to be absorbed into the oceans, or for trees to turn it back into oxygen, which is the primary methods. So until we plant more trees or get more surface area of the oceans, which isn't happening anytime soon, we're going to have to find ways to cut down carbon dioxide if that's a cause of global warming. But there are other greenhouse gases too. So water vapor is one, but it's not a heavy greenhouse gas because it's not in the atmosphere very long. Sulfur dioxide is the same way because it comes out as acid rain. So it doesn't hang out in the atmosphere, it tends to hang out on the ground instead after it rains. Well, what are the gases that are the major greenhouse gases? These are the 7 that everybody's worried about. And what we have here on the right-hand side is the 100-year global warming potential, or what we call a CO2 equivalent, okay? And normally we measure this in metric tons of CO2 equivalent. So first off, we have carbon dioxide, which is 1 unit of CO2 equivalent. Then you have methane, which is the predominant feature of natural gas. If methane just emitted by itself into the atmosphere has a global warming potential of 25 times CO2. Then you get into nitrous oxide, and then you also get into then your hydrofluorocarbons and perfluorocarbons, which is all the stuff that you see in air conditioners and dry cleaners, for that matter. If you have an air conditioning leak, you're leaking these hydrofluorocarbons all over the place, which is 14,000 to 15,000 times worse than emitting carbon dioxide in the air. So number one thing you want to be able to do is make sure your air conditioner is not leaking. An industrial process where you'll find that is in all the chillers that you use. If you're using a chiller with R12 refrigerant or R22 or something else like that, those are hydrofluorocarbons. And if you have a leak in your system, that's bad. You want to fix that right away. Also, you'll see in industrial sites that air conditioners are installed in electrical cabinets. You want to check those and make sure those aren't leaking. If you have a leak in any one of those, fix it immediately, because it makes your carbon footprint horrendous right away. Other one is sulfur hexafluoride. That is actually used a lot in magnesium processing, and it's the worst one there is. And it's used in magnesium processing to make sure molten magnesium doesn't have a event, as we like to call it in the industry, where it flashes and starts to burn. And it's only one of the only gases you can use, so that means magnesium processing is very, very, very carbon intensive, even though it doesn't use carbon dioxide, because it has a very high greenhouse gas potential. So moving on, combustion. A lot of times, this is the IEA, which is the Industrial Heating Equipment Organization. I've got surface combustion on my shirt. Surface combustion manufactures combustion-based furnaces and electric furnaces. We're about 50-50. But combustion simplified, why we have to worry about this is we're taking methane which has a global warming potential of 25. We're reacting with oxygen and nitrogen, which is air, to produce heat, 1,000 BTUs, and we're also producing carbon dioxide. So combustion is a very important, fire has been very important to humankind for a very long time, but it emits carbon dioxide. So what can we do to make sure that we're emitting as little as possible and make sure we're as efficient as possible? And what other technologies can we use to reduce the amount of combustion that we have to do? So that's what we'll get into next, and how we calculate our carbon footprint. And just as a sidebar, this may be a little of a political thing, but US and industry in general are doing their part in carbon footprint reduction. US overall, since 1990, our carbon footprint has gone down by 7.9%. But you hear about around the world that it's gone up, and that's mostly to do with other countries, but the US has done pretty well. And honestly, industry has done pretty well. If you take a look at the right-hand side graph, the carbon footprint of industry has gone down by 13.7%. What's gone up is the amount of carbon that's been emitted by transportation and agriculture for good measure. So that's why there's a lot of focus right now on transportation, because that is the largest emitter of hydrocarbons. And we're looking at the electrification of vehicles, which is a good idea, but will help reduce the US carbon footprint by quite a lot. So we'll talk about why that's good later on. So let's talk about greenhouse gases and scopes. You'll hear a lot with greenhouse gases, things called scopes, scope 1, scope 2, scope 3. Scopes have to do with the greenhouse gas protocol, a corporate accounting and reporting standard. That is a document that was released in the early 2000s, used as the basis of accounting for greenhouse gases. The EPA has adopted this, as well as most of the countries around the world, as the de facto standard for accounting for greenhouse gases. And the way they do it is they define different scopes of greenhouse gases. And what are those? Number one is direct carbon emissions. These is things that you're burning fuel on site, it's natural gas, oil, gasoline, and you're emitting carbon dioxide or other greenhouse gases to the atmosphere. Number two is indirect emissions, and that has to do with purchased electricity. So what's the carbon footprint of the electric power you use? Also has to do with purchased steam and purchased heat. The third event is the indirect activities, stuff that's happening upstream and downstream of the plant. And there's many, many different impacts there, but the most important thing is a lot of people in their initial reactions to having to calculate their carbon footprint are focused solely on scope 1 and maybe on scope 2. Scope 3 could be 90 to 95% of the greenhouse gas emissions for a company. So only focusing on scope 1 and scope 2 is a major mistake, and you're going to be undercounting the amount of carbon your company emits. So again, just summarizing, scope 1, direct emissions, scope 2, indirect emissions that from sources that are controlled. I can control how much electric power I use. I control how much purchased steam I use. But indirect emissions, it's from things I don't really control. The stuff's coming into my plant with a carbon footprint, and after it leaves my plant, someone's going to use that and generate a carbon footprint with that as well. So it's not directly tied to something that I can do. The scope 3 emissions, there's 15 categories, and you can see them here. The ones I always find interesting is business travel and employee commuting. Employee commuting, I believe, is on the employee themselves, but at the same time, it's part of the corporation's activities. The ones I think are really important here are waste generated by operations, transportation and distribution, and the use of your sold products. Because depending on your process, you might be using an inefficient process, or you might be using a process that adds value to something that allows carbon reductions downstream, and you have to take account for that in your carbon footprint. That's a minus. That helps you get closer to net zero by understanding how your products are used and what the alternatives are. So let's talk about calculating your carbon footprint. So I've set this up into five steps. And most of these steps, or I believe, are for a company whose thermal process is the predominant source of their carbon footprint. If you're just an office building, this is probably not the right way of doing it because there's probably other things that are more important. But if your primary emissions are from a thermal process, this is how I would do it. I use it doing the 80-20 rule, Peter's principle, whatever one you want to call it. This is what I would do. Number one, find your natural gas bill for a year. Go down to accounting, go down to purchasing, find it. Step two, find your electric bill for the year. Again, same place. Just go down there and figure it out. Step three might take a little bit more work. Find out how much processed gas you buy each year. That's the nitrogen, oxygen, hydrogen, the stuff that comes in bottles or in tanker trucks that you're putting into your plant. That's a very critical piece of the carbon footprint for every thermal process. Step four, look at the odometers of your truck fleet. And then you can add in your fork trucks if they're propane powered or if they're electric powered even. You want to take a look at that because moving stuff around has a carbon footprint. In step five, evaluate everything else, which is all the other scope 3 stuff that we haven't considered in the first 4 that you want to take a look of. But if you look at the first 4, that will be 75 to 80% of your emissions most likely. So step 1, your natural gas bill. If you take a look at your natural gas bill, your utility will probably report how much natural gas you're using in the CCF or MCF. And if you take that number and use these two equations and multiply it by this, what we call an emission factor, 0.05444, you'll figure out the metric tons of CO2 equivalent that you emit each year or each month, depending on your bill looks like. So that is the number one thing to look at. So for example, then, here's my personal electric bill from last month. My electric utility is Columbia Natural Gas, and they just happened to tell me how much natural gas I used in last year in my household. So I've used 973 CCF. So I take my handy dandy formula, I put 973 in there, and I find out that my household emitted 5.3 metric tons of CO2 equivalent over the last year. Okay, well, I didn't know that before, now I know it. I don't know what to do with that information, but I know it. So let's move on. I made it 5.3 metric tons of CO2e. That seems like a lot. I don't know if it's a lot. We'll find out. Electric bill. So go the same thing, go to your utility and figure out, well, how much power did I use last year in kilowatt hours? Then you have to multiply it by another emission factor, which is different based on your power source, where you are in the country, or where you are in the world. So let's go into what your emission factor will be for you personally. So electric power system, there's many, many different sources of power. There's solar, wind, hydro. Those and more or less have zero carbon footprint. You can say that they probably have some because it takes carbon to make solar panels, takes carbon to make wind turbines, takes carbon to make a dam, especially a lot of cement. And there's a lot of carbon dioxide in cement production. And there's a lot of carbon dioxide in nuclear power and making a nuclear power plant. But operationally, they're saying the carbon footprint of the creation of electric power for those 4 is 0. But if you're using coal power or gas and fuel power to create your electricity, that electric power has a carbon footprint. So what is that? In 2020, the electric utility and independent power producers, the emission factor for coal is 1.0118. Natural gas is about 40% of that number. Petroleum is about 5% less of that number. And geothermal actually has a carbon footprint. This is the energy you get from steam in the ground, from geysers or whatever. And it just so happens that there's some carbon dioxide stored in the ground. And when you bring it up, it will emit. So it does have a little bit of a carbon footprint. But those are the ones you have. Now, solar, wind, hydro will all be 0. So you could take your kilowatt hours and multiply it by 0 and you didn't emit any carbon due to electric power. But if you don't have 100% renewable energy, you have to multiply by one of these factors. Just so happens though that there's a bunch of different power plants on the grid. It all gets blended. And when it all gets blended, you can't tell which power source it came from. So what do? You go to this handy dandy map that the EPA provides to figure out what your emission factor really would be. I live in Ohio, so I am in the RFCW, which is RFC West District, and I can find that my emission factor personally, because we have a lot of coal-fired power plants, natural gas-fired power plants, we have windmills and solar as well, but predominantly it's coal and natural gas. We also have nuclear. So if it was 100% natural gas, my emission factor would be 0.4111. But I'm not, so my emission factor is 0.4468. Now, if I live somewhere else in the US, like say in Virginia and the Carolinas, where in Duke Power, they have a lot more nuclear, my emission factor would be 0.2626. If I was up in Quebec, in Canada, my emission factor might be 0 because it's mostly hydroelectric power, or in the TVA region. So depending on where you are in the United States, you're going to have a different emission factor based on where you live. Globally, your emission, it's also based on where you live globally. In Canada, they have a lot more hydropower than we do, so their emission factor is much lower relatively. France has almost 80% nuclear power. So in France, it's pretty simple. You should go electric for most of your thermal processes. Same thing in Sweden. Sweden is the only country I know of that is 100% renewable energy. The only part of the emission factor they have is mostly from geothermal. China is much worse. They're mostly coal power, so they have 1.52, same as India. I always find it fascinating. Japan is worse than the US because I think of them as cleaner, but they have to import a lot of liquefied natural gas to generate their power. So what's this all mean? Here's my electric bill. My electric utility, it's Toledo Edison, First Energy. And they say on my bill that over the last 12 months, I've used 12,279 kilowatt hours of electricity. And I know from where I live, my map, that my emission factor is 0.4468. Now I'm assuming that all the electricity I use is baseload electricity, which probably isn't exactly true. Because when it gets to the peak summer months, we all know that all these extra power plants have to come online and it's non-baseload, which means the emission factor for those non-baseload hours are much, much higher. So really my emission factor is probably in between 0.4468 and 0.8212. But for this example, I'm just using 0.4468. And that says I'm emitting 5.49 metric tons of CO2 equivalent from my household for the last year, which is more than my natural gas bill, which is kind of surprising. So I emit much more carbon from electricity than I do from natural gas. The other thing you have to think about as an industrial plant is power factor. Utilities charge customers for the amount of gross power they use. Power factor is something they use to figure out what your net power is. It's a power you're actually seeing turn into energy or into motion or into heat. And power factor comes down from a level of 1 based on inductive loads. The more inductive loads you have in your facility, the lower your power factor is, and the more you're getting charged for power you're not using. So what causes your power factor to decrease? In the case of thermal processing, induction heaters. Induction heaters drag down power factor by a lot. There's things you can do to create filters and rectify and all these other things to help increase that power factor. But if you have an induction heater in your facility, you have to pay very close attention to your power factor, because even though you might be using only a certain kW of energy, you're actually, just the way these vectors work, you're using a lot more according to the utility. The other thing you have to take a look at is what the efficiency of your transformers are. And then also, do you have any very large motors? Especially in cases of when you have a high pressure gas quench, those motors can get up to 1,000 horsepower. That's a pretty big motor, and it could, if you're not careful, it can reduce the power factor of your facility. Another thing to keep in mind is natural gas and electric power loss rates. If I have a natural gas utility, I'm going to lose from the wellhead to the electric utility entrance. There's going to be 7.6% of the natural gas in that pipeline going to vent to the atmosphere somehow through a leak or something else. That's pure methane that's not been burned off. So that has a global warming potential of 25 times the electric utility emitting it in the form of CO2. Now, there's also natural gas loss between the wellhead and the manufacturing facility entrance. But because it's just a little bit further, there's not much more lost. So that's important to keep in mind. The other thing is electric power and transmission distribution. For every kilowatt of electricity that an electric utility generates, 5 to 6% of it's lost in transmission over power lines. So you're losing your natural, if you have a natural gas fired power plant, you're losing natural gas before you get to the electricity. You're using electricity after it leaves the plant. So therefore, you're actually not getting a lot of the power that you out of the natural gas that you originally intended to get. So let's move on to step 3. Purchase gases for purging, process atmospheres, and cooling. And in this case, if you're creating an atmosphere from natural gas, or if you're creating an atmosphere using a pressure swing absorption type of generator for nitrogen, you've already accounted for those things in the previous 2 steps. You already figured out your natural gas bill. You already figured out your electric bill. But the gases, other gases that come into your facility, the nitrogens, the argons, the hydrogens, the ammonias, the acetylenes, the methanols, all have a carbon footprint due to their method of production. Nitrogen and argon are made with air separation units. So it's the same thing with oxygen. And those you have to use lots and lots and lots of electric power, and it depends where that electric power comes from. Newsflash, most of it is coal and natural gas. Hydrogen, ammonia, acetylene, methanol are common industrial gases. Those are all made with natural gas for the most part. We'll talk about that. So here's a comparison of carbon footprint of nitrogen that's been delivered versus on-site generated. This is for a general one of my customers. They're going to be using maybe 6,000 standard cubic feet of nitrogen a day. They might have a 1.1 million standard cubic foot capacity tank outside, and they're going to have a truck to deliver that. And the truck is going to be using fuel and going over maybe 300 miles. That's how close my nitrogen facility is to my nitrogen facility. So a truck has to travel 300 miles to fill up my nitrogen tank. So I have to account for how much gas that truck is using. And we'll find out just by holding nitrogen on site and by having it delivered and having it vent with regularity, my carbon footprint of that nitrogen tank is 9.08 kilograms of CO2 per hour if I'm using 6,000 standard cubic feet per hour. And then that has to be produced somehow. And using that, the air separation units have to use electric power to do that. Most of them, some use coal, but a lot of them use natural gas, and a lot of it. And in general, if you're using natural gas, that's going to be 0.4111 for your emission factor. And with the amount of electricity you use, that's 47.36 kilograms of CO2 per hour that's going through with my nitrogen. So all told, if I'm using 6,000 standard cubic feet of hour of nitrogen, I'm emitting, not myself, but because of the feedstock I'm buying already has it, I'm technically emitting 56.43 kilograms of CO2 per hour. On-site generation, you're going to be using electric power to generate your nitrogen on site. So it depends on your level of electric power on site versus at the gas company, which one's better or worse. You hear a lot of things about hydrogen, and there are different colors these days. And here's just a chart to kind of show what that is. Most hydrogen is made with technology called SMR or ATR. SMR is steam methane reforming or autothermal reforming, which basically is taking natural gas, cracking it, and taking the hydrogen, and then using the carbon for something else. But most of the time, it's being emitted as CO2. So gray hydrogen has a carbon footprint of about 24.1 megatons of CO2 per million standard cubic feet. You can also generate hydrogen from coal, and that is a predominant method in China, and it's only about 25% of global supply. In the US is about 70, the gray hydrogen is about 77% of what we produce. Newer technologies, you have blue hydrogen, which actually has carbon capture and sequestration. With that, you can maybe capture 50 to 90% of the carbon dioxide out of that process. It's not a very high industrial use production yet. Same thing with green electrolysis hydrogen, needs tons and tons of electric power to do electrolysis of hydrogen. Only way you're going to do it, if you have 100% renewable electricity, you're making green hydrogen. If you're making a nuclear power, you're making pink hydrogen. But technically, that hydrogen does not have a carbon footprint if you're using clean electric power. Then there's gold hydrogen, which is hydrogen that you use based off of biofuels or biomass. And that's used the same thing using carbon capture and sequestration. That supposedly has a zero carbon footprint. However, if you way you account it, like the biomass is just going to landfill anyway, you can actually claim a negative carbon footprint for that gold hydrogen. And then there's another one called turquoise, which I believe is manufactured by BASF, where actually it takes solid carbon instead of taking gaseous carbon dioxide and putting it into caves somewhere underground. They're actually taking the solid carbon and putting that in somewhere. So if as a customer of mine, normally might be using 6,000 standard cubic foot per hour of hydrogen. If they're using it in their process, they'd be emitting, if they're using gray hydrogen, 205 kilograms of CO2 per hour, which is 4 times more or less than nitrogen. And then if you did blends of nitrogen and hydrogen, that would all kind of come out to somewhere in between those two numbers. Other atmospheres that are produced by steam methane reforming, I'm not going to go deep into this, but ammonia, methanol, acetylene are all made using natural gas. So they're going to have a carbon footprint before they even get in your plant if you're using these gases, and that's what the numbers would be. And on top of that, if you're burning off acetylene and methanol, they're going to have an emission at your plant as well, because you have to burn them off. Because otherwise, if you don't burn them off, you might be emitting methane, and if you emit methane, that's 25 times worse than carbon dioxide. So you want to burn it off. So more or less, here are the emission factors, scope 3 emission factors, not scope 1, not scope 2, scope 3 emission factors for various process gases and atmospheres. And that's kind of just summarizing what we just talked about, of things we can, and there's some assumptions stated there below. Based on my conversations with people, they're pretty valid assumptions, and these are pretty good numbers to use if you're trying to figure out the carbon footprint of industrial gases in your facility. If you want to know the specific answer, talk to your industrial gas supplier. I know for a fact they can tell you these numbers. So these are the numbers I've calculated, and I know the industrial gas suppliers that I've talked to, the numbers are pretty close. So maybe 1 or 2 or 5% off, but they're pretty darn close. So step 4, transportation. I don't use any process gases in my household. I don't use any oxygen, thank goodness. So I omitted that out of my calculation, but transportation is important to me personally. And trucking is probably a huge factor for most thermal process providers. And here's our emission factor per mile for different things. You can also figure out how many tons of product you're shipping around the country and use this 0.211 kilograms per ton mile factor as well. But if you want to figure out the metric tons of CO2 equivalent, multiply the amount of miles on your odometers or that your trucks are driving times the emission factor in this table, and you'll figure it out. For me personally, I got 2 vehicles. One vehicle is my wife's. She drives at 8,000 miles per year. I drive mine a little bit more, about 12,000 miles a year, total of 20,000 miles a year. We both have SUVs, extremely light passenger cars. Sure, might be a little bit of a reduction of assumption, but more or less that means we're emitting 6.64 metric tons of CO2 equivalent per year. That's how you figure that out. And so that's more than my electric, and that's more than my natural gas. So for right now, I'll say if I want to reduce my carbon footprint, number 1 place I want to focus on is transportation. So step 5, we're talking about other categories. There's many thermal processes with inherent process-related carbon dioxide. Cement production is another one. Those guys are going to have a real hard time decarbonizing because one of the things in the material itself is carbon dioxide, and it gets emitted, and the only way to get rid of it is to sequester it. No matter if it's electric, if it doesn't matter if it's natural gas heated, you're still going to emit carbon dioxide. And there's nothing you can do about it if you want cement. HVAC usage and leakage, we talked about that earlier. You want to take a look at other purchased goods, especially water. Oils and glycol also have a carbon footprint, so you want to pay attention to that. Waste generation, wastewater has a major carbon footprint, and I'll show you that on the next slide. And you also want to take a look at trash. In general, I don't have data for industrial facilities, but I know for me personally, for a household of 3 people, I'm probably emitting somewhere about like a 0.5 metric ton of CO2 per year on just on trash. And it depends on how much you recycle. If I didn't recycle at all for my household, luckily my city has a huge recycling program, it might be about 1 metric ton. So waste generation at your industrial facility is a little bit different than waste generation of a household. So you can talk to the people who's your trash and landfill to figure out what your number probably would be. And then we already talked about business travel and employee community, but another one I just want to hit again, I haven't read in there, is the downstream processing, use, and end-of-life treatment. A lot of thermal processes actually add value to a part. They make stuff last longer. They make stuff, and when you make stuff last longer, it means it's out in the field longer, which means it takes a longer time before it has to go to landfill or if it has to be recycled. So it saves thermal energy long term. So you can make a claim that if something lasts longer because of what you're doing to it, you're actually reducing the carbon footprint of the world. Now, that's a big statement, and you better be able to back it up. But there's definitely certain things. If you're increasing the fatigue life of something, you're increasing the corrosion resistance of something, that has a positive carbon footprint impact on the world, and you should try to take credit for it. So just wanted to talk about wastewater. Wastewater is 5% of global greenhouse gas emissions, direct cause, and 30 to 40% of local economies are using their electricity for wastewater treatment. So I put this here just so everybody knows what this is. If you know how many gallons of water you're using per year, it's about equal to how many gallons of water you're wasting each year, and it has to go through a wastewater treatment plant. So if you have something for your water bill, you can figure it out. I live by Lake Erie. I don't have to transport water very far to get to my house. However, I live in New York City. I got to multiply numbers in this equation by 1.5 because I'm getting my water from 300 miles away on the New York City aqueduct. So that's very important to keep in mind because that takes pumps and electricity to transport that water. Not as many because it's mostly gravitation in New York, but other places it takes a lot more electricity. And then if you're desalinating water, you have to multiply it by 2.2. If I'm in Dubai and I don't have green power and I'm burning oil to desalinate water, that's a much larger carbon footprint than by just pumping it out of Lake Erie. So here's my water bill for last year. I used 774 CCF of water. I multiply it by the emission factor I just calculated, and that's 1.45 metric tons of CO2 equivalent. Now, it's not very much compared to the other categories I calculated, but it's still something, and probably means I should not run my sprinklers as much in the summer. So anyhow, so summary, here's my carbon footprint using the 5-step process, and anybody can do this at the same thing. I did this in a couple hours. If you have your utility bills and you have the amount of purchased gases and you know how much your fleet drives, you can figure this out. And so, and with that, more than likely, that's going to be 80% of the answer. All this other stuff that you want to do, figure out, is going to be much, much harder to find, and it's going to be much lower of an issue for you. So the first top things you want to work on are these items right here. So I got my carbon footprint now. What do I want? What can I do with it? What should I do with it? So we want to talk about reducing your carbon footprint. So what do? First, I'll set a SMART goal, something that's specific, measurable, achievable, realistic, and time-based. tell yourself, okay, by 2035, I'm gonna reduce my carbon emissions by 25% and set about doing that. Some things, honestly, makes that a really easy goal to achieve, honestly, if you take a look at efficiency. And if you put efficiency first, you can reduce your carbon footprint by a lot. You can also consider other commercially available solutions for carbon neutrality, purchasing carbon offsets, purchasing renewable energy. Those are all good ways of doing it. And then considering new technologies. So we're going to talk about all these things in a couple slides to kind of show you things you can do. So lean manufacturing, it's all about reducing waste, reducing waste, reducing waste. Reduce waste, reduce the stuff that's input into the system, so you reduce the outputs from the system. Reduce, 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 you're halfway there. But if you get a 10% reduction in any of these categories, you're on your way to a 10% reduction in your carbon footprint. And then reuse waste heat. Use heat recovery devices. Use recuperators. Use regenerators. Find ways to use waste heat so that you can take credit for the heat in that gas before emitting the carbon dioxide. Every bit of waste heat that you can use to enhance your process means less carbon, theoretically, that you're emitting to the atmosphere. So what I always tell people is the number one place that you can get carbon emission reduction is tune your burners. If you have burners on your furnace, most of the time, over time, they become untuned and they're operating at very high excess air for some reason, or they might even be running rich. Go through your facility, tune your burners. You might see a 25 to 30 to 50% reduction in your carbon footprint overnight. I want to say it again. You might see a 25 to 30 to 50% reduction in your carbon footprint overnight. Tune your burners. Next thing to do is minimize your furnace losses. Furnace maintenance equals carbon footprint reduction. If you maintain your furnaces, you fix gaps, you fix missing insulation, you will be able to keep the efficiency of that furnace up to par, and you will reduce the carbon footprint of your facility. Also, you want to reduce the amount of thermal cycling you do, the amount of times you have to heat something up and cool something down. The more you heat stuff up and cool stuff down, you're releasing stored heat in the walls of the furnace. And by releasing that stored heat, that is getting emitted out into the atmosphere, and it takes carbon to heat it back up. So reducing the amount of thermal cycling you can do is better. Keep your furnaces at one temperature and one temperature only. And if you do that, you're pretty good. And then use recuperation, regeneration, like I said, and do stock preheating with waste gases. There's lots of different ways to do that. If you want to talk to a furnace manufacturer, they can give you really good ideas of how you can do stock preheating with your waste gases and reduce the emissions that you have. Other things you can do is oxy-fuel combustion. Instead of using air for combustion, use oxygen, and you'll be able to get more intense heat, and you'll be able to emit less NOx for sure. And also, it actually makes carbon sequestration and separation easier, because all you're doing is if you can find a way to get water out of the system, all your bits left is carbon dioxide, and that you don't have all the nitrogen that you have to pump out of the way too. So that's actually a benefit of oxy-fuel combustion if you can do it, and you want to take a look at carbon separation technologies. However, as we talked about earlier, cryogenic nitrogen has a carbon footprint, and cryogenic oxygen is going to have a higher carbon footprint than that. Because the same way you make cryogenic nitrogen is the way you make cryogenic oxygen, but there's less oxygen in air. So you have to account for the amount of carbon being put into the oxygen before you even burn the fuel to see if it makes any sense. Alternative fuels is another thing to look at. A lot of people are talking about methanol these days as a greener fuel, or biofuel and biogas. Here in Japan, they're mostly taking a look at ammonia, because Japan is a very high LPG usage rate, and they're finding that they can use ammonia much more efficiently. And maritime industry is looking at using ammonia on ships, burning ammonia on ships instead of diesel fuel. In the US, we're mostly concerned with hydrogen. With hydrogen and ammonia, you're not emitting CO2, but both gases have a carbon footprint currently in the way they're produced before you actually use them. And then hydrogen burns hotter, so you're going to have more thermal NOx associated with it. And ammonia contains nitrogen, so you're going to have more chemical NOx associated with it. So you're trading one thing for another, but depends on what you're looking for, what your goal is. And here's just a slide for hydrogen for heat. This is a big thing these days. Everybody's talking about blending hydrogen into natural gas lines or using hydrogen for heat. Today, it's not there. You're going to emit about 50% more carbon burning hydrogen than if you burn natural gas. Now, as more green forms of hydrogen become available, that number is going to decrease. So maybe it becomes less than natural gas. But right now, because you're making hydrogen from natural gas, it's going to have a higher carbon footprint when you burn it than natural gas. It just goes to reason. So if you're blending hydrogen into your natural gas line, well, you just increase your carbon footprint, and you're kind of not doing, if your goal is to reduce carbon footprint, you're not doing it. And that's just, all burner manufacturers these days build burners for hydrogen use as well as natural gas use. So hopefully over time, hydrogen will become much more efficient, the production of hydrogen become much more efficient, and then the amount of CO2 being emitted from a SCF of hydrogen will come down. And that's just the chemical equations if you want to know chemistry, but there you go. So carbon footprint reduction methods, carbon capture, storage, and sequestration and storage. If you can remove CO2 from the process of combustions and store them somewhere else, then you don't emit CO2. Question is, how do you do that? There are methods to do it. For the average user, you're not going to be able to afford it, and they're not really made for low usage. If you're a huge industrial facility, possibly you can use carbon sequestration, but right now this is on the oil refinery level, not on the individual furnace level, almost even the steel mill level. So you have to, this is down the road a bit, but eventually, hopefully you can use something like this. But the question is then, where are you going to put the stuff? It's going to be underground, and hopefully it doesn't leak, right? And also when you do that, you're going to have an energy efficiency penalty because you have to pump carbon dioxide places and move it around. In general, when you try to do stuff to save emissions, you're going to have an energy efficiency penalty. So you have to pay attention to that. Here's just a couple tables, just courtesy of Bloom Engineering. They've done a really good job over the last couple of years showing how different methods of combustion can either save carbon footprint or maybe even add to the carbon footprint. I'm not going to go through these numbers right now, but pretty much a table on the left is pretty much telling you tune your burners. If you're operating in high excess air, you're emitting 30 to 50% more carbon dioxide than you should be. And then also then on the right-hand side of the table is showing what happens if you have a cold air supply system versus a recuperated, regenerative, or an oxy-fuel system. And it also shows the amount of electricity required for oxygen, to create oxygen for an oxy-fuel system. So you'll see in this case particularly, an oxy-fuel system has a higher carbon footprint than a regenerative air system that operates at 1775 degrees. So again, if you work with your burner manufacturer, utility, your furnace provider, they can help you make these calculations to figure out if I'm going to make a change to my system, will it actually improve my carbon footprint or not, or could it possibly make it worse? Along that line, electrification. A lot of questions right now from customers of mine to convert their furnaces from natural gas to electric. And the first thing I ask them is, where is your power coming from? If you don't know where your power is coming from, if your power is fossil fuel based, it is a terrible idea to electrify if your goal is carbon footprint reduction. If your electric power supply is highly renewable, then it makes all the sense in the world. However, you have to, so current furnaces, the furnaces in your plant right now can be made to run electrically, and it's not a problem. However, a lot of times you're going to have to derate the furnace. It's very hard to fit as much electrical power, heating power into a furnace, the same size furnace as gas power. So unfortunately, I don't have an exact number for you because it depends case by case, but you're going to see maybe a 10 to 20 to maybe a 30% reduction in total power, heat power to the furnace when you transform to electric. But if you have a green electricity, it's probably worth it, even though your production rate might fall down. Here's something: furnace efficiency, electric versus natural gas. Typical power plant is going to be 30 to 45% efficient with how they burn fuel. Same thing for an internal combustion engine in a car. So if you got a car that has a 35% efficient internal combustion engine, and you got your utility with a 35% efficient electric power source, well, more or less it's a net neutral switching from a gas vehicle to an electric vehicle. And most likely, since the electric vehicle is going to be lighter, it's going to be a net positive for the environment. So going to electric vehicles is a really good idea. Going to electric furnaces sometimes isn't a good idea, because furnaces can burn natural gas much more efficiently in general than electric power producers can produce electricity. And that chart there kind of shows that if you're using cold combustion air, the crossover temperature is about 1800, 1850 degrees, where electric starts becoming the preferred method of doing it. However, if you use recuperation, you're not going to see a benefit or reduction in carbon footprint using electric power until you get about 2250 degrees or more, which is getting to really high temperatures in general for most thermal processes. So going on, we got a couple minutes left and we're almost done. So for electrification, the number one thing is don't make the greenhouse gas problem worse. If you have high fossil fuel usage, use natural gas. If your electricity utility has high renewable usage, use electric. You got a bunch of waterfalls and dams around you, go electric all day. If you're in the middle of West Virginia and all your power plants are coal-fired, go natural gas. It's the best way for you to optimize your carbon footprint. There's also alternative processes, vacuum furnaces, induction heating, infrared heating, all good methods. It all just depends on what you're trying to solve. Vacuum furnaces, you're gonna have less idle time losses because you just turn them off. They're electric. You're gonna have less processed gas usage, but you're gonna have higher wall losses during runtime, about 5 times more than a refractory furnace. And also you're gonna be thermal cycling those furnaces all the time. You have to heat them up and cool them down to ambient temperatures before you open them, where you don't have to do that with an atmosphere type furnace. Induction heating, great, perfect, wonderful thing to do if you don't have any controlled atmospheres required, but you do have to consider the power factor issues now, like we talked about before. Infrared heating, great for low temperature, thin section surface heating applications, is definitely something to consider if all you're trying to do is just heat the surface of something, especially at low temperatures. So finally, we're talking about commercial options to reduce carbon footprint. Green power, you can buy green power. You can talk to your utility and buy green power. You can talk to an independent producer and buy green power. Or you can buy renewable energy credits from your utility. That is something you can talk to them about. You can also purchase carbon offsets or carbon credits. Carbon offsets are actually probably a little bit easier to get. You can buy them now for $8 to $18 per metric ton CO2 equivalent. That means if you got a million BTU per hour gross operating furnace that's operating at 24/7, 365, in general, you're emitting 465 metric tons of carbon dioxide a year. The cost to offset that is only $3,700 to $8,400, which on an operating hour basis is 42 cents to 96 cents an hour. It's not a lot for a lot of processes. So it might be, if you want to get carbon neutral really fast, which is what carbon offsets are meant to do, buy carbon offsets. And there's a number of different places you can buy them at. Now, if I want to personally become carbon neutral tomorrow, I can go to a place and buy a carbon offset of my 18.88 metric tons of CO2 per year and pay $151 to $340 per year. So if I really want to be popular at cocktail parties, I could do that and say, hey, I'm net zero, good for me. So, and you can do that too. So that's an easy way to do it. It's not sustainable long-term, but if you want to do something right now and say you're net neutral, which is honestly what a lot of people are doing, this is how you become net zero tomorrow. Final thing, this is just a slide to show ways to reduce your carbon footprint of thermal process in summary. And if you can take a screenshot of it, these are tips I tell everybody. These are the #1 things you want to do to take a look at to reduce the carbon footprint of your facility. All right. And with that, I want to say thank you. And if there's any questions, I'll open it up. And Kelly, if there's anything that came across, I'm happy to take them.
Yeah, thanks, BJ. We did. We had some questions and comments, and we actually have Michael Stowe on the line too. He's available. He's gonna lead some Q&A. We'll just answer a couple questions here, but attendees can also reach out to us at IHEA if they have additional questions, since we're pretty short on time at this point. But yeah, Michael?
Yeah, one interesting question, and we hear this a lot, I'm sure you do too, BJ, was is my scope 3 somebody else's scope 1 and 2?
Yes.
Yes, absolutely. So you know, one person's trash is another person's treasure. So
Yes.
if I'm making parts for an automotive company, for example, I have scope 1 and 2 to make a head valve cover gasket or some gear or some tire for a car company. Well, then when the car company adds up all their scope 3, they're going to have to count for what my carbon was to make the tires that they bought and put on their car. So yes. Any other comments on that, BJ?
The way the whole this system works is they try to avoid double counting. Okay. So it all comes up to who the OEM or the government is at the end of the day. So you have to think of this as a tree structure. Each individual branch on the tree or leaf on the tree is going to have their carbon footprint, and it all rolls up to the end use, right? So, but it's important to know what the preceding steps are, and honestly, it's important to know what happens afterwards. If you don't know those things, you don't know the true impact you're having. Now, again, you want to make sure when you add it all up, you're not double counting anything, right, on a global basis. But based on what you can control and what you have impact on and what you can change gas suppliers. You can change if you can change if you're getting vegetable oil-based products versus crude oil-based products. There's lots of different things you can change that you are in control of that really comes into play in the scope 3 and accounting for your scope 3 emissions.
Thanks. Just looking down a little further. Let's see. Are bottled gases considered part of scope 1 emissions?
Bottled gases are not. Bottled gases will be part of scope 3. And that's why I put them in there. Unless you're using, bottled gases are produced upstream of your facility, right? And they come into your plant, but they're not recyclable. They just get emitted after usage to the atmosphere and are not recoverable. That's why it's important to know what you're doing with them, because they're just gone, right? And then they have to be regenerated again. So they're scope 3, but again, the scope 1 and scope 2 emissions of the gas plant, the person who creates a gas, becomes your scope 3 emissions.
Yeah, thank you. Here's an interesting question. When figuring the impact of your trash, does it matter if it's compacted or not?
Well, it all depends on what's decaying, right? If I'm a restaurant, I'm going to have or a grocery store, I would say my carbon footprint's a lot higher because I have food waste that's decaying and emitting carbon dioxide. I think food waste is a huge impact in the world, from what I understand. For as industrial sites, a lot of times you can recycle oils. You can do a lot other types of recycling with a lot of industrial waste. When you get into like a steel mill or something like that, they have certain fluxes and all the dross and things like that. That kind of just sits somewhere, but is it doing anything? Is it emitting anything? No. But it's really all that digestion by bacteria that's emitting carbon or methane or anything else, which is why you see flares at landfills, right? Mm-hmm. So that is the carbon that's getting emitted. And why you have flares at landfills is if you don't burn it, you're emitting methane. So if you burn it, you're reducing the carbon footprint by 25 times by turning it into CO2.
Okay, what about when you're looking at your carbon footprint, what time period or duration should you look at? A year, past, baseline, future? What kind of type of duration should you focus on?
Best practice is focus on 1 year and then use that as your baseline. So you take your baseline year, 2020, 2023, you count everything for that year and use that as your baseline year and set your goal off of that year for some time in the future, 2035, 2050, 2060, whatever, saying, I'm going to reduce my carbon footprint by this amount by that year, right? So then you can measure it, it's timely, but you also have to make sure it's smart. You have to make sure it's actually achievable, right? Because you don't want to be heading out there with a goal that just isn't practical. And like I said, there's a number of things you can do right now that makes it instantaneously achievable. One thing I don't want to have happen personally is have a goal out there that it's just a blanket goal. Everybody's got to reduce their carbon footprint by 50%. Well, that is not a very good goal, because if I'm a very inefficient producer, a thermal process producer, I might have my burners operating at high excess air, and I got another producer operating their burners right on ratio, and that person who's been doing it right all along is going to get punished because they can't reduce their carbon footprint as much as the other guy and as easily. So it's very important to have the right metrics to be using to figure out. You want to look at total overall carbon footprint per pound of production, not just what are you emitting today or tomorrow.
Maybe one more, Michael, one more question?
Yeah, one more question, and actually we just have one more. Is it okay to consider only carbon dioxide kilograms in your carbon footprint in place of carbon dioxide equivalent for heat treat processes?
For most part, yes. Okay, and that's what I did in this presentation is I mostly just considered carbon dioxide. If you have any sort of natural gas leaks, you need to consider carbon dioxide. You need to consider that as a carbon dioxide equivalent. For the most part, that's not an issue. Your methane and your nitrous oxide production is going to be a lot lower. It's going to be maybe less than 1% of your total CO2 equivalents. But there are some processes where it's going to be a lot higher. So you have to keep that into account. Just have to be mindful of it. It's not just CO2, there's other gases involved. And the one you have to pay particular attention to is all your HVAC. You have to pay attention to all your chillers. You have to pay attention to all your coolers, all those heat exchangers that have refrigerants in them. If those are leaking, that's a big problem. You need to fix that today. But make sure you account for it at the beginning so that you can claim credit for reducing your carbon footprint later.
All righty, and just one question about the presentation. It is going to be shared or available, Kelly, is that correct?
Yes.
Yes, this is being recorded. We will post it on the sustainability page of the IHEA website, www.ihea.org. And I would like to thank BJ so much for his information today, and Michael as well for fielding all the questions with us. And remind everyone, please watch for the link after the webinar here. We would love for you to fill out our survey and provide your feedback. And also, we will have the remaining 3 webinars in this series, one in June, one in July, and one in August. Of course, they are listed on the website as well. So go ahead and register for those now so you get the link to watch that webinar. So thank you, everyone, and have a great afternoon.
Thanks, everybody.
Bye-bye.
Bye-bye.